Hi everybody, this is Sriniti, Krishna, and Jerry, and this is our final project for ECE 3140. For this project, we wanted to build an interactive LED board, something that responds to what you draw in real time. The user draws directly on a Pygame interface running on their computer, and whatever they draw appears instantly on the LED board. As you can see, each pixel on the Pygame grid maps directly to a pixel on the LED board. Users can choose from a variety of colors: red, orange, yellow, green, blue, purple, or white, and it can also erase just by right-clicking and dragging. It's a simple but powerful way to interact with hardware through software. Now I'm going to talk a little bit about the structure of our setup. We have four main components: the Pygame interface with the UART connection, the FDRM board, the external serial LED board, and finally the LED display itself. Starting off, as you saw earlier, we built a custom drawing interface using Pygame that runs locally on the laptop. Users can draw and select colors directly in the interface. Each time a user selects a pixel, Pygame sends a corresponding character over the UART. For example, R for red, G for green, and so on. These characters are passed along to the FDRM microcontroller. The FDRM board receives the color codes from the Pygame through the UART and acts as the bridge between the software and the hardware. The board then forwards these signals to the small external serial LED breakout board. We use this external serial LED board to connect the FDRM to our custom LED display. Specifically, we soldered the wires from our LED strip to this board so that it could relay the color data properly. Brings us to our LED display. For this, we used individually addressable LED strips from Amazon. We cut and soldered the strips to form a 17 by 14 grid. Since the LEDs are addressable, we can control each one individually, letting us display the exact pixel and color from the Pygame interface in real time. Here's another example that showcases all the available colors from our interface. So putting it all together, Pygame sends a stream of color data via the UART to the FDRM board, which passes it to the external breakout board, and finally to the LED grid, allowing us to display rainbows or any other pattern in real time.
So next we're going to go into a code overview of this project. So code was located in two main places, the first one being on the FRDM KL64Z board, and the second one being a Python Pygame file. So on the FRDM, we had three main files, the first one being a low-level assembly file, which sends RGB data to GPIO pins with very precise timing. The second file was setup.c, which sets up the UART, it receives data streams, and lights up the LEDs. Lastly, we had led.c, which contained functions to set up an interface with all the LEDs. And the low-level assembly file and led.c were both files provided in previous labs. Next, we only had one Python file, which was canvas.py, which actually starts up the interactive canvas and also sends streams of color data to the FRDM by UART. Next, we're going to go into testing and challenges that we faced during this project. So testing was split into three main phases. The first phase was actually building the board. We went into the lab and soldered the board ourselves, and we also used prior lab code to determine the maximum number of LEDs that we could light up, which ended up being 238 LEDs. Once we were able to get the board lighting up, we had to establish a UART connection, and we had to ensure that the board could read data that was sent serially over UART from a Python program. And once we were able to do that, it was just figuring out LED logic on the board with the received data and actually lighting up the LEDs. Now we're going to go into some of the challenges that we faced in this project. The first one was setting up UART connection. This was a very difficult challenge. We had to enable specific registers for receiving. The next challenge was turning on LEDs with 20.9 megahertz. 20.9 megahertz was the internal clock frequency, and that meant we had to modify the number of no-ops in old lab code to ensure that we had the precise timings to make it work. Lastly, we had to process incoming streams of bytes. This meant we had to load incoming characters into a buffer array. And once that buffer array was full, we would finally send that information to the LEDs and actually light them up.
Thank you so much for watching, and we hope you liked our project.